So last time we had studied this Gauss-Jordan method. So it's again elimination, but this time we used it to find inverse of a matrix. So what was the idea? You take a square matrix, and I'm again taking an example. And you write on the other side the identity. Then you perform any allowed row operations on this whole thing. And your goal is to get to the identity matrix on the left hand side. And by the time you have identity on the left hand side, the right hand side where you started from, the identity matrix itself would have turned into the inverse of the starting matrix. So this guy is your given A, and here you have put an identity. You turn it into identity using row operations. When you do that, this turns into the inverse of A. So if I do this for this matrix, I'm just gonna first bring zeros over here, so I'm not doing anything to the second row. And then I just subtract this row from the last one. I get -2, -2, and I'm subtracting this row from here. So I get a -1, 0, 1. Now I can
Sir, row 3 column 2 positive 2 नहीं होगा 4 minus 2 2
-4 plus 2 is -2, -3 plus 1 -2. So I can make this bring a 1 over here. To do that, I just multiply the last row by -half. And now, again, this is my pivot. I bring a 0 here. I get this thing as it is. And now I'm just subtracting row 2 from row 3. So I get a 0, 0, half, -1, -half. Now, what do I do now? Because I'm trying to make an identity. Over here, I'm now stuck with a 0. So I don't have a pivot over here. If I do anything, if I add this row back down over here, it's gonna mess up this row, this column. I don't want anything to be created over here. And I know what's happening. I cannot change it because I have got a complete 0 row. So that means I cannot make an identity over here. So then how do I find the inverse? What happened to the inverse? So the question is, did this method fail to find an inverse? Well, it did fail, but what does that mean? Yes, but what does that mean? By the way, you should also note, it's just a reminder that when you get a 0 row in a square matrix, that means you have less than, if you have like 3 variables over here, only 2 of them are lead. And one is like the third, in this case, the third one is the free variable. So one thing you can immediately say about this coefficient matrix is that if I think of this as a coefficient matrix of a linear system, it will not have unique solution. Solutions not possible. So that's just a side remark, but it would be important. You want to answer that this method seems to be failing in some cases. What does that mean? Well, if you go back to these equations. So if I take this same matrix A and write an equation like this for any B, what I can do is I say if A inverse exists, then I can multiply the both sides of A, this one, by A inverse. That means X is A inverse B, and if A inverse is unique, then the solution is unique. So if the A inverse is unique, then the solution has to be unique, because solution is necessarily, this is necessarily the form of solution. There is no other solution. X, if this equation is satisfied, then X must be A inverse times this matrix B, one unique matrix. But we can easily show that the inverses are unique. So suppose you have, let's say, B1 and B2 are inverses of a matrix A. Then by definition, this means B1A, AB1 is identity, but also the second matrix is also inverse. We're just assuming that we have two inverses, for example. then these both equations will be true. These 2 and 3. But then I can multiply equation 2 by B2. Well, let me multiply from the left. So I have this B1A is equal to identity. I multiply from the right by B2. But B2 is inverse of A. So this gives me identity. So that means B1 has to be equal to B2. So I don't have two matrices. If I assume two matrices, they are same matrix. So the inverses are unique. Or I should say, there is only one inverse. One inverse, if it exists, one or no inverse for each matrix. So we have proved this thing. Let's call it a little theorem. If A inverse exists, so there's only one inverse, so that's why we just denote it by inverse, because it's a unique matrix. Exists, then AX has a unique solution. And we have already proved it above. So our coefficient matrix we just saw over there, it had a zero line. That means it didn't have a unique solution. But if A inverse exists, then it had to have a unique solution. So the only possibility is that the A inverse does not exist. So this method failed only because A inverse did not exist. So you will not be able to, if you encounter that you have a zero row when you are trying to make an identity over here, that would mean that this matrix doesn't have an inverse. If you recall the row echelon form, reduced row echelon form. So you have things like this. Can you turn off your mic, please? Over here, above every one, you make zero, something like that. But the point is that if you have we are only considering the square matrix for now. If you have n by n matrix, at maximum, you have n lead variables, right? And if you have n lead variables, you have only n rows. And in the row echelon form, each leading non-zero number is a 1. So if this is the case, if number of lead variables is n, then necessarily reduced row echelon form will look like what form it will take. You have n rows available and n lead. So in each row, you have to put 1 like that. You do not slide. You cannot put 2. You cannot slide it by an extra 0. So on the diagonal, you get 1s. But in the reduced row echelon, you also start making zeros above the lead ones, and you can always do that. So that means the reduced row echelon form is identity. If the number of lead variables is equal to n. But when the number of lead variables is equal to n, then you have a unique solution. If you do not have a unique solution, then you will have, for example, m, which is less than n, free variables. And only n minus m will be lead. तो आपका जो मैट्रिक्स है यहाँ पे तो ऐसे है. For example, even if I put something like this, for example, I'm looking at a 4 by 4 and I have 1 free. So one of them will slip. इसके ऊपर सारे 0 कर दिए, इसके ऊपर 0 कर दिया, बट यहाँ कुछ भी हो सकता है. So you will have a 0 row. Then x3 is यहाँ पे is free. And you have a 0 row. तो जितने आपके फ्री वेरिएबल उतने ही 0 rows होंगे. So the conclusion is, if the solution is unique, for this guy, then A की जो reduced echelon form है is identity. But from this you can conclude, this implies, if this is so, then A must have an inverse. पहले हमने इसके opposite show किया था. If A has an inverse, then this equation must have a unique solution. But now we're going to prove that if this equation has a unique solution, then A must have an inverse. So over here we have showed that if this equation has a unique solution, then the reduced echelon form of A must be identity. But as we saw last time, that we can get to this form by performing, we know that we can get to this form by performing row operations, but those row operations we can accomplish by these elementary matrices. So by a sequence of these elementary matrices, I can turn this A into I. But this equation is saying that this product is just A inverse, because when I multiply these matrices, I get a single matrix E. That multiplied with A gives me identity. So that matrix must be the inverse of A. So since I showed that I can transform A into I using row operations if the solution is unique, and that transformation can be achieved by multiplying with elementary matrices, so I can find an inverse. So I have proved this theorem. So the combined theorem I can write let's write like this. AX has a unique solution, has unique solution if and only if by the way, just to write it in a shorthand, if and only if people write it like with double F's. This means if and only if A inverse exists. And this B can be anything. So sometimes people write it, it's kind of more useful to specialize to a simple B. And people write it for the homogeneous case. That this guy has no non-trivial solution, because if it's a unique, then it has to be the zero solution. Solutions if and only if A inverse exists. So is there any question? I left. So I grabbed the wrong notebook, but anyway, I think let's do it without the notes. It's not that hard. Let's have a quick look at the determinants. So what's the point of determinant? So we have seen that some matrices have inverses and some don't. And the way to find an inverse is again solving the linear systems. Using row operations, the same methods which you use to solve a linear system, they give you inverse because those things are equivalent. If you have inverse, you have solved the system. So you can find the inverse by doing these row operations, but there is a function associated with matrix. Given a matrix, you can associate a number with it, which will directly tell you that if this matrix has an inverse or not. So what is that? So if we go in turn, so first of all, if I think of just a number, A is a matrix. So it's a 1 by 1 matrix. then I know that inverse does not exist always. Inverse exists if A is not 0. So we will be looking for some number associated with the matrix, which when not equal to 0 will signify that this thing has an inverse. So you can say that the determinant of this matrix A is just A, the number itself. And if it's not 0, then it has an inverse. And the inverse is just 1 over A. Now suppose if I have a 2 by 2. This is again some new matrix A, 2 by 2. And I want to see that if it has inverse or not. The method, the original method, the main logic is that you have to convert it using row operations into an identity. If that can be done, then it has an inverse. If it fails in the sense that the reduced echelon form of this A is not identity, then this matrix does not have an inverse. If the reduced echelon form is identity, then it has an inverse. So we just try doing that. To do that, what can I do? So suppose, first of all, let's suppose, because we know that in the pivot over here, we want something non-zero. I don't know, I'm just keeping it completely general. So, but I will consider two cases. So suppose A11 is not 0 by chance. Then what can I do? I can divide this row by A11, multiply by A21, and subtract that from row 2. Right? This is what I need to do. Well, let's write here. To start making it into a row echelon form, reduced row echelon form, I have to multiply the first row by minus A21 over A11 and add to this. So I get a 0 here. Over here, I get minus A21, A12 over A11 plus A22. So this becomes A11, A12, 0, A11, A22 minus A12, A21, and then A11. Now I'm assuming that A11 is not 0. So this guy, if I want, I can multiply this row by A11 as well. Then this guy will be erased. It doesn't matter. You can leave it there if you wish. Now, if the inverse has to exist, then I should get a non-zero number here. Because if I get a non-zero number over here, I can convert it into 1 by multiplying by the inverse of that. But if I get a 0 here, I'm stuck. I'm stuck with a 0 row, and then the inverse will not exist. So inverse will not exist if A11, A22 is equal to 0. So that means starting with this 2 by 2 matrix, well, for now I have this special condition that A11 is not 0. Given that, starting with any arbitrary matrix, 2 by 2 matrix, I can make this combination and check if this is 0 or not. If it is 0, then the inverse will not exist. Otherwise, it will exist. So this becomes that function which I was after. So I just call it determinant for the 2 by 2 case. So multiply the diagonals, then subtract and multiply the off diagonals. Now suppose let's consider the other case. Can you please turn off your mic? A11 was 0. Then what would happen? Then A is of this form. But I can then exchange these rows because I have to bring a pivot up there. And now assume that A21 is not 0. If that is not 0, now what I need is, if A21 is not 0, and I don't want then for inverse to exist, what condition you need? कि यहाँ पे क्या होना चाहिए? Over here. When will inverse not exist? When A12 is 0, then inverse will not exist. For inverse to exist, well, let's write it the other way. Let me say the inverse will not exist if A12 is 0. Now since an inverse will exist if A12 is not equal to 0. Now since A11 since A21 we have assumed is also not equal to 0, then I can multiply this thing by A21 and it's still not 0. So I can change this condition into this condition. This is equivalent to this. But I had assumed that A11 is 0. So I can add to it this guy. This will not be 0 because this guy is already 0. Doesn't matter if I add this to it. So that means the determinant which I had defined earlier covers both cases. So I should still define this determinant as this. And then I don't care if A11 is 0 or not. It will still compute, it will still give me the condition that if the inverse exists or not. Well, the last assumption which I want to remove is this. So when I had assumed that A11 is 0, what if A21 is also 0? Well, then you are stuck with two zeros and you don't have a pivot. So you cannot convert this matrix into the identity, and the inverse will not exist. And since A11 and A21 are both 0, your determinant will still be equal to 0. So determinant covers all these cases. And that's the main job of determinant, telling you if the inverse exists or not. Now you can escalate it to 3 by 3. Now what will you get here? Again, I start with assuming but this condition won't matter because finally the formula we will get will cover even if this is true. But if we start with this and I'm just trying to go to row echelon form. तो अब आपने यहाँ क्या करना है, आप ये कर रहे हैं माइनस A21 ओवर A11 करके यहाँ ऐड कर रहे हैं और माइनस A31 ओवर A11 करके यहाँ ऐड कर रहे हैं. I should probably write it in a much bigger matrix. So, G, why I'm not using numbers? Because I'm just doing it in general, not taking an example, just doing a proof. So you have minus A21 into A12 over A11. And over here, A11, A23 minus A21, A13 over A11. And in this corner, all you are doing is replacing this with 3, 1. So you have A11, A32 minus A31, not A11, yeah, A11. This was A. So you have minus A3, you will have a term minus A31 times A12. And from downstairs, A11 will get multiplied with A32. And over here, you will have minus A13, A31. And from downstairs, you will have A11, A33. Now, what you're gonna do? You want this guy, you're assuming that A11 is not 0, and you want to make this matrix, convert this lower matrix starting from here, this number, and you're gonna start making this into identity. So that would be true if this determinant of this guy is non-zero. So when you do that algebra, what you find is the usual thing, that you need to have for this matrix, you need to have A33 minus A23, A32 minus A12, you just delete this row and this column. Minus A23, A31. So this gives you the condition that this must not be 0. And you can then try to remove this condition. If you go through what I did before, all of those things can be repeated. And finally, I can define, well, let's just write the definition of determinant once and for all. So you define this Mij, you define the determinant recursively. So if you have a matrix n by n, then determinant of A is just I should probably use some other symbol. Yeah, let's call it where these guys this is where Mij, where M, well, I should write it. Remember this one I over here and one I over here, these are not the components, not the components of this matrix. Rather, this is the name. This is label or name of this matrix. That means if I'm talking about A13, that's a name, that's a particular matrix A13. It's label of this matrix. Then there's A23, A12, A11. These are not the number in the first row and the third column of this matrix. That's just the name of this matrix. Similarly over here, this is also label of M and not the components. And what is this? Now finally I have to tell you, I've told you that start doing this. Well, I should keep going. It's a n by n matrix, so it will go until and what are these guys? This is n minus 1 times n minus 1 matrix where you delete the first row and the ith column. From your original matrix A. Original matrix के में से ith first row or ith column delete कर दें, start constructing this and start constructing these, and then this will be the expansion for the determinant. So if we take an example, I hope this 0 will not make it. So the formula says, take the first row, take this 3, then multiply it with minus 1 to the power 1 plus, this is the first column. So 1 plus 1, 2, and then compute the determinant of this guy. Delete this row and this column and compute the determinant of this. So the determinant is of this guy I know is 3 into 0, 0 minus determinant of this guy. Then take the second element, minus 1 into 1 plus second column, and determinant of delete this and delete this. Now we are at the third column, so delete the first row and the third column. and you get this determinant is 0 minus minus 1. So everything becomes, so this becomes minus 1, and I get a 1 from this determinant. This was minus 1 square, so this gives me plus 1. This is minus 1 cube, gives me minus 1. The determinant is 3 minus minus 1, so it's a 4. And 1. So I get 3 minus 4 plus 2. 1. So that's a determinant, which is not 0, so the inverse will exist.
I'm sorry.
G.
Sir, is this a formula for calculating determinant for matrices that are not 2 by 2?
Yeah. So it works for any dimension because the way I defined over here, it's defined recursively and in n by n dimensions. So for example, I will not compute it completely, but let me write it out. So suppose if you have this 5 by 5. Well, 5 by 5 would be too big. Let me just write 4 by 4. 9, 8, minus 1, 1, 2, 4. So according to this formula, determinant of this A would be take this row and start expanding in its elements. So 1 into minus 1, basically then just start with 2. And then the determinant of this guy. Delete the first row, first column. Then the second element. Then delete the first row and second column. Then 4. This is not 2, this is 3. You keep increasing it. And delete the first row, third column. This is a determinant. Determinant of this. And then the last one. 3 times minus 1 to the 5 and determinant of 0, minus 1, 2, 1, 7, 9. Now you have to do this job. Compute the determinant of this 3 by 3, again using this formula. So very soon it becomes very cumbersome. And actually in practice, it's a perfect formula. It's like a one single liner in writing it out algebraically. It's in a sense, it gives you a fixed algorithm that what you have to do with the different elements in the matrix. But computing it is very, very hard because as you can see in this 4 by 4, now I have to compute the determinants of all these 3 by 3. And it keeps increasing when you consider bigger and bigger matrices. So in practice, when you have large matrices, using Gauss-Jordan is still easier to decide if this matrix has an inverse or not. And it has an added benefit that it computes for you the inverse at the same time. But it's good to know that this formula exists. And by the way, this can be even generalized. So determinant is kind of proving these things is going to be like very time consuming. So I'm just going to write, and it's not very interesting. So I'm just going to write the generalizations. So over here, I wrote it, I expanded it in the first row. You can expand in any row. So you can say determinant of A जैसे यहाँ पे मैंने किया है I fixed the first row and then expanded in these cofactors. So you can fix any row. So this is the row, and then you expand like this. Where again, these aij's, they are defined as -1 raised to the power I plus j, जो भी इनका label है, and then this matrix, which you get by deleting ith row and jth column, which should be true because what you are doing over here. So for example, I started with this row, expanding in this row. But if I do a row operation, replace first row with the third, I know that's an allowed row operation. So it's not gonna change if this matrix has an inverse or not, because it gives me an equivalent system. So I can very well expand in terms of this row. So first take it above and bring that down. So if you take care of these possibilities, you get this generalized formula. And in fact, you can also show that you can even expand in column. So I fixed a row here. You can fix a column. And the formula for aij is still same. So this expansion will still work. So this essentially tells me the determinant of A, because if I expand it to columns or if I expand it to the rows, I still get the same answer. So that's telling me the determinant of A is same as the determinant of the transpose. So the only job, we won't be using determinants much, but the main job of this guy is just to tell you if the matrix has an inverse or not. There's also this thing, maybe I should talk about it now. Or maybe we will do it later. So let's do it. Let's stop here today and do this next time.
Thank you.